So today I'm pleased to introduce Cameron Purdy. Cameron is the founder and CEO of Tangasol, which was acquired by Oracle earlier this year. He has over 12 years of experience with Java and Java-related technology. He is currently the specification lead for JSR 107, otherwise known as JCache. He's here today to talk to us about Oracle Coherence Data Grid. This talk will be going out on Google Video, so please hold any confidential questions until the end. Cameron.
Thank you. So this is the presentation I'm going to do today is a little bit old. I just had it updated by someone to the Oracle format, so I know the slides pretty well, but it doesn't cover all the new stuff we've been working on for the past year. It touches on a little bit of it, and I'll probably dive into some of it without the assistance of slides. But if you do have questions as I go through, certainly ask them. A lot of the things that I'll cover in this are not specifically product tied, and then there are a lot of things that are obviously, I mean, everything I'm talking about is somehow related to what we do in our product, but a lot of it's more just general technology. And then, of course, there's a number of things I'll cover that are specific to what we do. This introductory section is fairly high level, so I'm going to run through this pretty quickly. Basically, when we explain what it is that we do and why it is that we do it, you know, there are a couple different ways to explain it, usually including graphs and bubbles and pictures and lines. But in general, you know, if you look over the past 10, 15 years, the amount of information that we're collecting, accessing, managing, archiving, auditing, storing, searching through, analyzing, rolling up, aggregating, and backing up, et cetera, has exploded. A typical system, you know, 10, 15 years ago, if you look at just the complexity of the schema, you know, you have potentially an order of magnitude, maybe 2 order of magnitude increase in the complexity of a schema under an application just in the past decade or so. You know, you used to get a database and it would come with 7 tables in the pub's example database, and you could run an entire business on it. Now a typical invoice object is represented by, you know, 170 tables. So it's, you know, you just look at the explosion of complexity of what we deal with. And part of it, too, is that, you know, when the internet happened, you know, systems that used to be call centers with 100, 150 people operating them, all of a sudden became globally accessible. We still had the same cruft sitting behind it, you know, the same mainframe system, you know, tied into the shipping department and the billing department and everything else. So we took green screen scraped applications that we had converted to client server for our call centers, and we converted them. Now we, you know, put another wrapper around it and made them available to the web. But the problem was we didn't have 100 or 150 people using it. All of a sudden we had, you know, potentially thousands. I don't know if you look at the statistics of usages on various transactional sites. It's a lot lower than you would imagine from what you read in magazines, but it's a lot higher than most people have ever dealt with. So some of the travel sites that we work with, for example, run about 40,000 concurrent users, which doesn't sound ridiculous. It's probably far less than the numbers that they publish. But it actually puts some pretty obscene loads. In one case, one of the 3 big ones, you know, they host just the hotels portion of their business on, I think, 300 servers, which, you know, if you consider the amount of work that 300 servers in aggregate can do, you know, each server having probably 4 to 8 cores running at around 3 gigahertz, I mean, that's a, let me change my French there. That's a lot of CPU cycles that are getting burnt to do relatively simple stuff. I mean, all we're doing is sticking text on someone's screen over a TCP socket. How hard can that be? You know, you look at the, no offense to Google. You look at some of the trends as well. I mean, everything we do as engineers, as we're inventing new complexity so we can rewrite what we just wrote a couple years ago. When you talk about virtualization, the ability to move apps around and spread them out across multiple machines, or pretend that one server is actually a whole bunch of servers. You look at SOA, where we basically redo the whole green screen transition, except now instead of a green screen, you know, it's some collection of code that we have, and we wrap it up and make it, the wrong granularity, so we have to call it too many times in a loop and, send back more information than actually is needed and things like that. So all we're doing, if you will, generation after generation of software is finding less and less efficient ways to do what we've been doing for a long time. You look at SOA as well, it introduces another kind of an analog to the internet in terms of the users of applications. When the internet happened, if you called up a call center and said, well, I need a ticket to Alaska, and they said, well, my computer's slow, right? Hang on for a minute. You don't know. They could be down for all you know. They could be like writing on paper. But when you go to Expedia or Hotwire, Orbitz, or any of these Delta.com, any of the travel sites, et cetera, and you start booking a ticket, if it's a 404 that you get back, there's no person saying, oh, my computer's slow. I mean, it's down, and you go somewhere else. So, your failures become public. Similarly, in an SOA system, if you're building a composite set of services and you're relying on other services, you find out that uptime isn't predicted by the uptime of a service. So, for example, if you build a composite service that uses 6 other services, you now have, assuming they all have 99% availability, you have best case scenario 93. You have 7 services that have to be running, all running. So it's 99 and 99 and 99. So you end up having to basically make each individual component 100% available to even approach the numbers that you would expect any business system to provide. And 93% availability means you're down for what, half an hour during an 8-hour window business day. So I mean, it's pretty pathetic. Or depending on your business, it might actually be pretty good compared to some systems. Event-driven architectures. I mean, this is death by 1,000 cuts, or 1,000,000 cuts, or 1,000,000,000 cuts. Being able to take information and have changes to information drive in an autonomic fashion to drive other transactions that change more data, that produce more events, that so on and so forth. So, you've probably read something about like staged event-driven architectures. What I'm referring to here is systems that basically take information that's being managed in transactional information, and as it changes, those changes drive other business processes, which create feedback loops within the data sets. So basically, all these things lumped together. If you look at the history of what we've done as an industry over the past 10, 15 years, we've basically massively increased our need for information for the applications. We've massively increased how much information we create, how much information we consume, audit, everything else. And at the same time, the traditional infrastructure for managing information hasn't kept up. I mean, we've doubled the speed or overall throughput of CPUs every, I don't know, roughly 24 months, 26 months now. It used to be 18, but it's not quite as good anymore. We've increased the number of CPUs we can put in a box, theoretically. But at the same time, those increases have not kept up with the other growth that we've looked at. So it's what we call a scalability chasm. Systems that have to be able to handle hundreds of thousands of, relatively computationally expensive transactions per second. Just as an example, things that just aren't conceivable on traditional infrastructure. And the way that we address the challenge is by lashing together a whole bunch of cheap computers and letting them work together. And so fundamentally, we're going to look at how we do that. So what's a data grid? Basically, it's something that manages information in a grid environment, lots of servers working together. But it's a little different from kind of a traditional grid where the servers run independently and don't really rely on each other. It's not a stateless infrastructure. It's actually an infrastructure explicitly designed to manage state. And as such, it has to be able to manage it, for example, transactionally. It has to be able to provide actual correct information, not just best guess or relatively recent. It has to be able to guarantee once and only once operations, even if server failure occurs before, during, after, whenever it occurs. So fairly high standards for what it has to be able to accomplish. And it also, when you add servers, it's really nice if you can actually do more with them. It's one of the concepts, I guess, behind the scale out term, which is you add more servers, you can manage more data. You add more servers, you can handle more transactions per second. And so we're going to look at how that works as well. I'm just going to skip this because it's marketing. Same thing here. I mean, this is basically what I've already said. I mean, this is what has really driven the need for our software. And if you think about it, just like step back from all the technology for a second. We started a company in 2000, which was dead center of the beginning of the open source revolution. And we actually sold software. And we sold enough software that we more than doubled revenues for 7 years in a row. And we're still selling a lot of software. And so like something that we did must have been valuable to someone, or those previous marketing slides that I skipped must have been really good. So there must have been some massive need, some massive pent-up demand for solving this type of problem. And if you look at the number of companies trying to imitate what we've done, I think it speaks for itself that there's a real market there and a lot of interesting stuff going on. So talking about data as a service, I mean, this is kind of a summary. What we look at, what we do in terms of our software is we provide these capabilities of managing information across a grid infrastructure. We look at that as a service. It's something that we provide to an application or to a series of applications. We do it in what we refer to as the middle tier, meaning it's not a database, it's not a GUI, it's somewhere in between. It can sit inside an app server. Our software's all, our implementation is all Java, so it sits typically in the same type of location as an app server would, might even run inside an app server. It also allows all sorts of things that haven't been previously possible, including the fact since it's working with a domain model, things like integration can occur at the domain model level as opposed from hacking directly against the 170 tables representing one of those objects. So it allows concurrency control and operational control at the domain model level. So what is a data grid? As I said, it combines data management and data processing. So it's not just being able to access information. It's actually also about being able to push processing to where the information is being managed in this environment. So a couple key points I think I cover in some of these slides. We talk about, I'm just going to skip around a little bit, see if I can find what I'm looking for. I think I lost some slides in here somewhere. We talk about what we call single system image, which is, it doesn't matter if I have 1 server or 1,000 servers. I need to see, conceptually, when the application asks a question, it needs to see the entire set of information. So for example, if I'm adding servers dynamically, I don't want to see information like disappearing temporarily and showing up somewhere else. I don't want to know what server it's on. I don't want to have to go to a particular server to get information. No matter how the information is organized within a distributed environment, I want to see a single system image. I want the software to lie to me and pretend that all the information is local. It doesn't matter if it's terabytes of information. I want it to pretend it's all local. So if I have to ask inefficient questions, they'll all be answered without having to have a knowledge of the infrastructure, what servers there are, what addresses there are, so on and so forth. So that's what's called a single system image. At the same time, it is a lie, right? It's a lie that it's all in one place. It's a lie that it's all local. Any sufficiently scaled system is going to have to spread that information out across lots of servers. So having done so, you don't want to fulfill the lie. You don't want to have to fulfill the promise of the lie, because what it means is, if you have a single-threaded process that says, how many items are there? I'm going to go into a for loop. I'm going to grab each one. Grabbing means dragging them across the network. Asking how many there are means, working with all the servers to figure out a sum. And by the way, you've got 100 threads running on 100 servers. That's 10,000 threads. What's the likelihood that that number is not going to change? In fact, what's the likelihood that it's ever, how many stars are there in the universe? There's no answer. Only God knows, because the concept of time in a distributed system doesn't exist. There's only relative time among servers. So all these concepts that you think about within a single-threaded system, which is how most of us have been fortunate enough to code, none of those concepts actually hold true, even in a multi-threaded system, let alone a distributed environment. So what we want to do, if we have all these servers managing information in concert, we want to be able to push processing to those servers. We don't want to have to drag information locally. Oh wait, let's create a transactional context first, drag it locally, work with it locally, put it back and hope we don't have to roll back and repeat the transaction, right? Why don't we just send what's inside the beginning commit? Let's just send it over to where the information is. And if we have 100 servers and we're processing information that's spread across all 100, let's just send it out to all 100 at the same time, push it out to those servers, let them process in parallel. So in other words, once you can achieve the guarantees in terms of information reliability and once and only once processing, it gives you the ability to much more blindly push information around and push processing around because you know it's actually going to get taken care of. You don't have to worry about what happens in the case of server failure and things like that. So fundamentally, when you build distributed systems, no matter what acronyms you make up for your internal projects, no matter what you read in some book written by a guy who's actually never built a working distributed system, I haven't written a book yet, so don't look at me. No matter what you call it, there's really only two things you can move conceptually. You can move state and you can move behavior, and that's it. Like I mean, fundamentally, you can only move bytes across the wire, but conceptually, you can only move state and behavior. So when you build a distributed system, most distributed systems today have been built around the concept of moving, well, messages. So basically, moving behavior disguised as state, if you will. In other words, telling another server to do something. We call it RPC. I mean, I went in the bathroom here, and there's something nice on the wall telling me how to simplify RPC. And I thought, oh my God, I'm going back to Corba days now. It's I assume this is public knowledge that you hang things in your bathroom telling people how to build software. But I mean, RPC is I mean, this is the way that we built distributed systems 20 years ago. And outside of very specific context, I would suggest that RPC should have stayed 20 years ago. And so what I want to show as well today is that a lot of what we attempt to accomplish with things like RPC is actually much more naturally considered as, for example, state transition. So it's state management, not so much just messaging, RPC, et cetera, but the ability to actually represent the things that we're doing much more naturally and efficiently and less error prone by managing state. So what I was saying earlier, I mean, managing information, you're either going to move the information to where your code's running or you're going to move the processing to where the information is sitting. The benefits of moving the processing, well, there's a whole bunch of benefits. Some of them I've already described, like the parallelization of work. If the information is spread out across servers, I can spread out the processing naturally as well. There's a whole bunch of other neat little things, like distributed transactions all of a sudden become much less relevant. Distributed transactions are a nightmare because they fundamentally can't work. I mean, the theory of distributed transactions, if you actually get down to the theory, you'll find that at the end of the theory where it tells you about how it works, the last little fine print on the theory is, by the way, this doesn't actually work. There's no way to make it work. You always end up in a situation with distributed transactions that you have to make one of two choices. Doesn't matter if it's two-phase commit, three-phase commit, four-phase commit. At the end of it, that else, that last else, the otherwise on the case, it drops down the default on the case. That last gotcha, you have to make a choice. You have two choices. You halt, let it be manually recovered, for example, or you make a blind, maybe educated, so maybe not necessarily blind, but you make some sort of heuristic decision. You make, I'm going to pretend that it worked. Oh wait, no, I'll pretend it rolled, pick one. Pick one. You either halt or you guess. So being able to eliminate two-phase commit, for example, is one of the keys, one of the very essences for producing continuously available software for transactional systems. In other words, if you cannot eliminate two-phase commit, by definition, you cannot create a continuously available system unless all the components are continuously available, which in reality doesn't exist. Even a mainframe has a parity error every 300 and something years. So, and user error much more often. Let's see. Oh, I should have also mentioned the second one. This is also extremely important. Based on the granularity of information, concurrency control can become a major factor in large-scale systems. So if I'm moving information around, whether it's transaction control or whether it's explicit pessimistic concurrency control, or locking service, if you will, if I have to move information around to manage it, so I have a local transaction running potentially in multiple places at the same time, either optimistically or pessimistically, or I have code that's actually locking information, changing it, and putting it back. In all these cases, I'm coordinating across multiple servers. If I can push the logic to where the data is being managed within a distributed environment, all the concurrency control can be localized. It's a fundamentally different way of looking at a problem that most people don't see until you get well past unit testing phase. And I have one example. I can't name any customer names, et cetera, but this ended up this problem of concurrency control and distributed transactions bit one of our competitors very badly because they don't have a consensus-based clustering mechanism underneath their product. They ended up having to use explicit concurrency control through transactions, and their throughput turned out to be about 2 transactions per second on the same hardware. By delegating the logic to where the information was being managed, we ended up driving somewhere between 200 and 250 times the number of transactions per second on the same hardware, with actually higher levels of availability and reliability. So, I mean, it ended up, because it's a much more natural way to do it, to push all the responsibilities related to the information to where it sits within a distributed architecture. And I want to get actually to talking about that. And this is the goal for pushing logic to information, which is locality. Just one more example before we dive into some pictures. One of our bank customers had 50 servers running a compute grid, doing a big risk calculation. It would take 50 days. So 50 days, if you're a bank and you have a month end, means that your calculation ends after your next month end. It's fairly useless. That's with 50 servers on the same hardware, so no additional hardware being utilized. We dropped the calculation to under an hour. So we didn't have any extra CPU cycles. So where'd the difference come from? It's very simple. Go back to your office after this and reboot your computer, go into the BIOS, and turn off your L0, L1, L2, and L3 caches. Actually, do it on your SMP systems that are running google.com, see what happens. When you reboot the computer, instead of being 40 seconds, it'll be 12 minutes or maybe 20 minutes. Right? Why is that? Well, main memory on an SMP system is like a database for an application. If I have lots of servers sitting in front of that database, it becomes a shared bus of information. And the information that the application needs isn't where the application is. It's only in main memory. There's no cache, if you will, in between. So by having the ability to move the information closer and closer to where the actual processing logic is occurring in the CPU, L0, L1, L2 cache, et cetera, the cache built into the CPU, the latencies on those accesses drop to an immeasurable level. On the latest Pentium chips, it's actually, I believe, less than a clock cycle for information access from the closest cache. So it's literally instantaneous. It's almost register speed, if you will. I think it's just slightly lacking in the parallelization side, but very, very fast. And so as you go back through those, you end up adding more and more latency to the point where it actually becomes measurable in terms of nanoseconds. And nanoseconds don't sound like much, but they add up in a hurry, as you would see if you did your BIOS tweak, as I mentioned. So all we did was eliminate I/O wait. In other words, those 50 servers, by having the information already on those servers ready to go, we had 50 times 4 or 8 cores each, right, times roughly 3 billion operations per second. Now normally, 2.9 or 2.99 billion of those 3 billion clock cycles would be sitting there in a sleep state for the CPU, because it's waiting on an IRQ to be triggered by a network card sitting on the PCIX bus, coming because there's something got received from an Oracle database or whatever sitting behind it. Just sitting there, doing nothing. 3 billion clock cycles. Why do you think you run more threads than you have cores? Because if you run 1 thread per core and you go to a database to get something or to a message service or whatever it is, you're just going to be sitting there waiting. The CPU is doing nothing. It's just cooling down from the last burst of work it did. So you have to run more and more threads just to keep your CPU busy, because the thread is typically spending 90, 99% of its time waiting on I/O. Similarly for these calculations, by moving the information into memory, all of a sudden those 3 billion clock cycles became usable. Not all of them, because in this case now we're in an SMP system. We had to wait on the main memory of the box, but much, much lower latency. So let's look at some pictures. I'm going to just start with where we started. Back in 2001, where we started was full replication. The customers that we were working with, we'd be talking to architects, developers, CTOs, whatever, and they'd say, well, if we could just keep the information in memory and keep it in sync across these app servers, we wouldn't have this problem. We wouldn't have to go to the database all the time. So we said, okay, we can do that. So we built a product and people bought it. And this is where we started. We would just replicate information across all the servers. So this picture is almost as old as the product, if you can't tell by the beautiful antiquated choice of colors. And basically, what it shows is a set of information, in this case, a unique key of A, B, C, and D, just for the fun of it, accessible by all the servers. So here we have 4 servers. Each one is able to access that information locally. In fact, this scales beautifully, right? If I can do 1,000 read accesses per server, and I have 1,000 servers, I'll still get 1,000 read accesses per server. The only problem is, on the right side, it scales abysmally, because now I have to update 999 other servers, which it doesn't matter how you do it. It doesn't matter if you use deterministic broadcast, doesn't matter if you use multicast, doesn't matter how you do it. Conceptually, it's expensive. At best, it's n log n. I mean, it's at best a good deterministic broadcasting algorithm. So that's actually not the major point, though. The major point is going from 2 servers to 2,000 servers, my capacity for information stays the same. If I have this much information and I fill my heap with 1 server, that much information is going to fill my heap no matter how many servers I have. So we haven't solved the scalability problem here, except for very small sets of extremely high read information. So what we did, notice the new pastel modern millennia colors being used here. So what we did is we partitioned the information. So same single system image, same API, same everything, but now behind the scenes, whatever information there is being spread out, load balanced, if you will. Let's pretend, just for sake of argument, even though this is purely pretending, that there's some magical system we built called a data load balancer, right? So instead of load balancing HTTP requests, we throw data at it and it spreads it out magically across the servers. In fact, it's really good because not only does it spread it out across the servers, but somehow it magically keeps track of where it's spreading it out to. So if we go back forward, it'll send us to that server. And not only that, if it decides that too much is going to one server, it'll actually somehow load balance it and remember all that too. So there's some magical pie in the sky thing that doesn't actually exist that's doing all that. And it's somehow doing it across all these servers. So no central directory, no master server, nothing like that. It's got completely, at the network level, it's completely peer-to-peer, no hierarchy or master server. But basically what it does is it provides the same logical view of information. It looks like all the information is local. This is the lie, right? Oh yeah, sure, I have 4 pieces of data. Now to say I have 4 pieces of data, I had to ask 3 other servers because I don't know what they have or don't have. And in fact, by the time I get the answer back, it could have changed, right? But I can answer the question, yes, I have 4 pieces of data, and if you ask me to iterate through them, I'll iterate through them and you'll see them as if they were local. But there's a cost to doing that. So what we've done is we've gone from free access locally from the replicated case, and here we have a fixed access because we have to go to another server, drag the data back, deserialize it, and give it to the application. Fixed. Why do I say fixed? Because it's 1 hop there, 1 hop back. Unless it's currently being load balanced so the server died, it's 1 hop there, 1 hop back. So in terms of gigabit Ethernet off the shelf, you're talking 76 micros to the switch, 76 micros to the server, 76 micros back, a couple thread switches, 700 milliseconds top end for simple access. And then of course it's deserializing using Java serialization, so add another 45 seconds and you get your object. I meant 4.5 milliseconds, sorry. It's actually a little faster now in the latest JDKs. Updating information, well, it sends it to the server that owns the data. So that magical load balancer that doesn't exist, it knows who owns the data. It's an unambiguous ownership. At all points in time, there's exactly one server, one and only one server, that owns that information. And that server, because it owns it, has to make sure that there's a synchronous backup, or however many backups we've been told to manage for this information. So until it exists on both that owner and whatever backups there are, it doesn't exist. And at that point that it does exist, this operation is complete. And even if failure occurs in the middle of it, which I think I have a slide for somewhere. No, guess not. They killed that slide. So even if it dies in the middle of it, this operation actually still finishes, and still finishes correctly. Partitioned, because it's partitioned, if I go from 2 servers to 2,000 servers, the amount of information that actually can be managed goes up linearly. Notice I said from 2 servers to 2,000, not from 1 to 1,000. So it's because if I only have 1 server and I go to 2 servers, I actually don't increase the amount of information I can manage because I now have a full backup. So one of them owns 50% and backs up 50% on the other, et cetera. Also, because of this magical non-existent load balancer, I know I can go directly from any server to any other server. So all the communication on the wire is completely point-to-point. Which for us is pretty efficient. We use UDP, which is just one skin graft greater than IGMP itself. So very, very efficient. Ownership is also extremely handy. It's non-ambiguous ownership because it also means there's someone responsible not just for managing the information, but when we start looking at pushing logic out to the information, that's the owner that's responsible for doing that work. So it's as if every piece of information, whether or not it even exists, right? Because I can also do processes against information that's not even there, like E. There's no E here, but it would land right here. I don't know. I'm pretending I know. But if it would land right here, it's as if there's a queue there for E with all the operations that someone wants to do against E. So all the concurrency control is done locally, et cetera. So everyone knows that if there's any operation against E, they would go to that particular server. And as you can see from these backups, there's always a plan in place what to do if a server dies. So everyone already knows that if this server died, any E operations would always go here or wherever, some other server. So achieving this, before I go on to the next slide, achieving this non-ambiguousness is actually probably the hardest part of what we do. I mean, the actual information management is relatively easy. Relatively easy means just, on the order of hundreds of thousands of lines of code as opposed to zillions. But knowing unambiguously, without having some sort of central service, et cetera, knowing unambiguously what servers are there, when they die, who's responsible for what, being able to do those things non-ambiguously. So it's being able to know that an answer is correct, being able to know what to do on failover, things like that. That's actually the difficult part. So what sits under this is a clustering protocol that we developed called TCMP, which, for those of you that have worked with distributed, well, I know you have, with distributed systems for years, it's actually quite inverse to the concepts behind traditional distributed computing. Traditional distributed computing, each server basically fends for itself. What we built is something where we consider each server to be completely disposable and we don't actually care if it dies. And it's what I refer to, at least from a marketing perspective, as organic clustering, meaning it's actually an organism. It's a multicellular organism. It's not a whole bunch of single-celled organisms. It's not a whole bunch of amoebas trying to eat each other. It's actually one living organism where each of the cells plays some role within it and are completely disposable. So, servers are not trying to protect themselves from failure. They're actually trying to protect the organism. And so what it means is that the services that we mount on top of it are designed explicitly. What they're communicating is the necessary information to make sure that they stay disposable. So at every point, any server can be killed. There's no central server, there's no master server, there's no whatever. I mean, all servers are equally disposable at any point in time. Near topology basically is, if you think of the partition topology as being like an L2 cache, near topology is like an L1 cache. Right? This is something that sits closer. It does two things. First of all, if I go and get this information and bring it back, I'm going to store it locally. So this is what we had before, the logical view of all the partitioned information. I'll store it locally. So if I ask for it again, I get it locally. So now I've returned to the latencies I had with replicated caching. Think of this as partially replicated caching, demand-based replicated caching. Now, how do I get rid of this information? Well, if it changes, I may not want to get rid of it. I may want to keep it around, and I don't care that it's stale. That's what we call expiry based. It's like, keep it for 5 seconds. One of our online gambling customers, they have a near cache that times out in like 1.5 seconds or 2 seconds. And the reason they do that is because the amount of communication, event-based communication, to keep it invalidated at peak loads on the site is actually greater than what Cisco can handle. Just the number of packets is overwhelming, at least prior to our bundling, our packet bundling implementation. And so what happens in that case is it's actually counterproductive to cache it. So they cache it for 1.5 seconds, which gives you good enough visibility. And then on a user-by-user basis, the session will actually overlay. So if a user does something that affects the information, before the transaction completes, it actually puts it into the session, hiding the cache data, so the user sees their own activity until the update actually comes back through. Yes?
What do you mean zero latency access? If data even in L1 cache, it's 3 cycles data. What means zero latency access?
So the question is, what's the latency for access here? So remember, this is all...
The question is, what means zero latency access? Because even data resides in L1 cache, it takes 3 cycles to get the data.
When I say zero latency access, I mean no network activity, no I/O, no deserialization, no... So it could actually be 40 seconds, because you could accidentally just ask for the information and then hit a GC. So, zero latency access in this case could be just by act of God, 40 seconds or whatever. Generally speaking, it's, roughly analogous to accessing some local data structure. The API looks like a hash table. It makes everything look like a hash table. So, it's roughly analogous, order of magnitude similarity in terms of performance characteristics. So zero latency, of course, is not zero from the point of view of the CPU designer. It's zero from the point of view of the application designer. So do you design CPUs or? No, I'm kidding. So yes, it's not exactly zero latency. It's just relatively zero latency. Events. So because you have an owner, if information changes, it knows who's interested in that change, and it sends out events to say it changed. So you can find out what it was, what it changed from, to everything else. You can listen to all the events happening to a particular data set, or you can listen to particular identities. You can filter them. You can say, I only want to see when things get inserted. I only want to see when a particular item gets deleted, whatever it is. The filtering, of course, occurs on the back end, eliminating the network traffic. And you can even listen to a query, which is really cool because we do parallel queries. So if you issue a query, it spreads it out across all those servers. They're all doing the local portion of that query, coalescing the results on the issuing server. And then the end result, if you combine that with the events on the queries, it creates a continuous query. Meaning you basically issue a query, you get back a data structure, a local data structure, a materialized view of what you queried. And that materialized view stays up to date. And by the way, it's the same API as everything else we already looked at. So you can actually sign up for events on the local, on the continuous query. You can query it. You can actually put a continuous query on a continuous query. Concurrency control. This is just explicit concurrency control. In the first case, the ability to, if you want to boil it down to the simplest possible way of understanding it, we manage in this picture, we manage a key that's A. We manage information that's a red-looking blob thing. But there's also other information that the system manages with it, such as who's listening to particular events. That's how we did the previous slide. We also manage who owns it from a point of view of pessimistic concurrency control. So all the information related to particular information in the system is managed almost in the same way, meaning it's all synchronously backed up. So you lose a server, you don't lose events. You lose a server, you don't lose locks. You lose a server, you don't lose your data. But basically, it means that we can very efficiently and scalably implement concurrency control. Transactions roll that up to units of work larger than individual items, so optimistic and pessimistic transactions, et cetera. Read through and write through. Basically, what this means is you have some underlying system that this information is being pulled from. So if you don't find it in your near cache, in your L1, and you don't find it in your L2, we just call the application back and say, hey, do you have A for me? The application sits on top of Hibernate, calls Hibernate. Hibernate goes off to, or Hibernate, Toplink, your own DAO, whatever code you want to stick in there. Goes off to the database, gets it, maps it into an object. We don't want to deal with any of that stuff. So once it's an object, though, we'll take it. We'll say, oh, thank you for the object. We'll store it here. We'll return it back. The nice thing about this is if I have a whole bunch of threads here asking at the same time for A, only one request goes across the network. And if I have a whole bunch of servers that come here asking at the same time for A, only one request goes to the database. And actually, in the latest release, it's even less than that, because it actually automatically tunes itself based on access patterns. It'll actually coalesce multiple reads into one. You know, the higher the load, the less number of database reads per cache miss occur. I think that's correct. Basically, it starts coalescing them together into larger and larger queries. Write through basically does the same thing in reverse. It writes it first to the database. Once it's in the database, it commits it to the cache. It's not a two-phase commit, though. Remember, two-phase commit means that we have to get to a point on the transaction control where we have to either give up and halt the system or choose the wrong answer half the time, right? So in this case, what we do is we require item potency. And this is, I should probably have a slide. I may have a slide in here on it. Item potency is actually the silver bullet of distributed systems. Item potency means, in software terms, it means you can do the same thing 10 times, 100 times, or one time and have the same result. You can think of it in terms of like an update where from a database point of view. I have a version 2, I'm changing it to a version 3, so I want to update that information, do all this work, where key is this, and version is 2, right? So if I run that update a million times, it's only going to change the information once. So I assume it would be once, just based on the fact I'm not going to explain the entire example. But in other words, item potency is a pattern of development where you build chunks of functionality that can be run an arbitrary number of times. Why is it important here? Because this server could fail before or after the database commits a transaction. And nobody knows. Well, God knows. Anyone here God? Okay. So you have to actually build a system that has to keep running with you not knowing what happened to that server. Did it commit it? Did it not commit it? You just don't know. The responsibility fails over to the other server, so it now has to write data out, but it doesn't know if it already happened or not. So the only thing it can do, if you want to eliminate the two-phase commit conundrum, is repeat the same operation. So it can only do that if the operation can be repeated blindly, because it doesn't know if the operation already went through or not. So item potency becomes a silver bullet for scaling reliable systems. So in this case, it fails over. It writes out the data again meaning item potently, non-destructively. So if the other one committed already, then this does nothing. If it didn't commit already, then it does the update. And so the end result is that we can eliminate two-phase commit in this scenario. Now, write behind caching is actually slower than no caching. I'm sorry, write through caching is actually slower than no caching, because it not only has to write to the database, but it has to manage the cache. So why would you do it? Well, easy, because if you're using read-through and write-through together, the cache becomes a veneer. So if the writes are low frequency enough, the cache always will stay up to date because the writes are going through the cache. So you're paying just a very little bit of extra to manage the writes, and then the reads stay free. So this is as opposed to the cache-aside architecture, where you would check the cache. If it's not there, you go to the database, you pull it from the database, you stick it in the cache yourself. That's a traditional caching approach. This actually interposes the cache between the application and the database, and as such, it actually can manage the consistency across all these servers of that information. Write behind basically inverts what we just looked at with write through. It writes it to the cache and doesn't care if it's in the database. So you change it once, it's in the cache. Change it 100 times, the latest version is in the cache. An hour later, it writes the latest version out to the database. So if I'm changing 100 times, I only have to do one write to the database. Not only that, if I change 100 items 100 times, I can batch it all up, write it all out to the database in one write. You know, think about session management. In fact, the original customer we built this for was Geico. This feature was driven by some of their requirements on session management. Their sessions are not HTTP sessions, they're user sessions for the lifetime of a customer. And so they would load the information from a database, store it in memory, manage it there, and then write it out to the database later. And they had a session server that they built to do this. Well, it only had to crash a couple times as a single point of failure before they figured out that was not a good idea. And basically their system evolved to the point where every HTTP request would load it from the database, parse it, because it was XML, of course, change it, and then write it back out to the database. Database under load, would read a structure that size. It would take about 200 milliseconds. To write it back out would take about 800 milliseconds, actually over 200, over 800. So you had a second per HTTP request for nothing, for absolutely nothing. Well, other than making sure it was in the database. And so the other thing was, I mean, their database was running then at 100% utilization during the day, when people were actually using the system, which gets really expensive. So what we did, since we can manage the information resiliently across multiple servers, eliminating the single point of failure, we would take those sessions, store them in memory, and then an hour later we'd write it out to disk. Now, how many customers would actually come along and do that many changes within, would stay on the site more than an hour? So basically it would read it one time and write it one time, regardless of what they were doing. And the end result was, something like 90-something% reduction in load on the database. And the latency, I mean, we just eliminated that 1,000+ millisecond latency. Because the access coming out of the near cache was 0, close to 0 latency. And the updates were just the cost of the XML serialization itself, which was about 23 to 25 milliseconds. So the end result was, extremely scalable through the partitioning and extremely efficient, from a performance point of view. And of course, I should point out, the reason that we keep 2 copies is so when one server fails, the other takes over the responsibility to write it out to the database. And once again, you have the same problem. Was it already written or not? You can't be 100% certain. So again, the same item potency requirement for the same reason. So what I want to talk about now is moving behavior. And so the first 2 examples on this slide are what I'll call old school. The first one is, and just so you know, the formatting on this is all, yes? 5 minutes. All right, well, this is the last interesting slide I have, basically. The first one shows how to basically send it to a particular server. I want to send, there's a server over there, send processing to that server. It's basically useless because everything else we do deals with state, not with servers. So the only thing that we use this for internally is JMX, because you manage servers, not state with JMX. The second one is, work management. So you create tasks, you throw them in, and it does it. We do this in our product. It gets used. It's really handy. But there are a million things that do this as well. JMS with a MDB is, in a lot of cases, just as good. The last one, though, is this pushing logic to where the information is. And this is what gets really cool. So let's go back to our 1.0 example of how to lock information and update it. Here's a sequential counter implemented in a grid. I'm going to lock it. I'm going to get it. I'm going to change it. I'm going to put it back out, and I'm going to unlock it. If you know the Java memory model, this is hardly different from synchronized, access the field, add 1 to it, put it back out, leave the synchronized block. Monitor enter on the way in, monitor exit on the way out. There you go. What happens, though, is this lock, remember that lock is information that we have to store on at least 2 other servers. So it's hop to the primary, hop to the backup, hop back to the primary to verify it, hop back to the requester. Now we're going to get it to the primary and back. Now we're going to update it to the primary, to the backup, to the primary, to the requester. Now we're going to unlock it to the primary, to the backup, to the primary, to the requester. That's 14 hops. That's a lot of hopping. So what if instead we just sent the whole thing inside the curlies? What if we just send that over, ship it over? So we don't have to lock it because it's lining up in that virtual queue sitting on that server for that identity. It just sits there in a queue waiting to be run. So I could have 10,000 servers doing this at the same time. It shows up there, it gets run, and all the running happens because it's coming out of a queue, virtually speaking. It gets run in order. So I don't have to lock it globally across all the servers. It's locked by nature of the data structure feeding the logic. So now it's 1, 2, 3, 4. It's to the primary, to the backup, to the primary, and back to the requester. So 4 hops instead of 14, 72% reduction in hops. Very importantly, though, is this. In the first example, from the time I lock on the primary to the time somewhere during this unlock, I don't know which step, so somewhere around 12 network hops out of the 14, no one else can do anything with that identity, right? It's like synchronized, right? I said no one else do anything with this. It's pessimistic. So if those 12 hops took, say, 2 milliseconds total, I just cut my transaction rate on this identity to 500 a second. Doesn't matter how fast I make my computer. Doesn't matter how many computers I have. 500, that's it, that's it. If I can eliminate that critical section, which is what we do with by sending the processing into those queues, all of a sudden, I can just line them up and start just chewing through them. So this is one of the ways that we achieve some of the transaction volumes, 100,000 plus per second sustained. I mean, because we're spreading the transactions out, they're all queued, there's no network critical section time, and it's just amazing. Not only that, but if I'm processing multiple things, multiple pieces of information, it's doing it in parallel. So here, just a set of identities to do it to, or a query to do it to. So automatic parallelization, still with the once and only once guarantees, which is pretty fun. So those are all scalar functions. So thinking in terms of, say database theory, incrementing a value is a scalar function. We also do aggregate functions. So this is a parallel aggregation capability. I want to go out and things like distinct, sum, average, et cetera. These are all things that occur just like the parallel query. They occur as much as possible locally with the information. Partial results come back and are tabulated by the requesting server. And all these capabilities, the processors and the aggregation, et cetera, these are all codable. That is, you don't have to just use the ones that we provide. So you can basically think of what we do as example code. So I have use cases and stuff, but I'd like to switch and see if there's any questions at this point, because I think we're basically out of time. That's all the interesting stuff anyway. Any questions? Yes?
So how do you coordinate conflicting updates to pieces of data that live in different places? And these updates are happening concurrently.
So how do you coordinate updates to conflicting updates to pieces of data that live in different places when they're happening concurrently? Well, the answer is they don't.
Okay. So I have to design this update so that they can happen in any order in order to use the system?
Well, the answer is that the data doesn't live in multiple places. There's one master copy of that information, and it is managed by the grid as a whole. I mean, specifically at some point in time, at each point in time, there's one server that owns it, and one or more servers that have a synchronous backup of it. But all the updates to that information occur in serial on the owner of that information. How do you ensure what?
How do you ensure that those two rights you do belong to the same owner?
How do you ensure that the two rights belong to the same owner? The rights don't belong to the same owner. The data is owned by a particular server. So the rights simply go to the server that owns the information.
Right, but do you need to like... You want to do a single transaction that updates pieces of information that reside on two different servers. How do you do that without two-phase command?
Is that the same question you're asking? So how do you update two pieces of information atomically that are spread over two servers? Well, fundamentally, it's impossible. So it's a by partitioning it across multiple servers, that level of theoretical atomicity cannot exist. Now you can simulate it so that the application thinks it's entirely atomic. There's the all I can think of is Gordian knot. No, it's a Lamport clock. There's the Lamport clock approach, multi-valued concurrency control, et cetera. But in reality, there is no such thing as an atomic operation across multiple servers. So we don't even attempt to pretend that there is. What we do is we actually, because we created the clustering protocol itself, we got to define the laws of our physical universe. And the laws in our case are based on in-order reliable messaging from each point to each point. So it's a fully peer-to-peer system. So if I have n points, from every point to all n-1 points, I have in-order message delivery, and they are reliable, well, guaranteed for the lifetime of the member.
From every point to return to a single client. What is two clients? updates to two pieces of data in separate places?
Well, the way that we do the transactions, if it's an optimistic transaction, one of them or potentially both of them roll back. Both of them would roll back only if there's a deadlock, if you will, potential deadlock in the pessimistic locking that occurs as part of the transaction two-phase commit. In the pessimistic case, one of them would either wait or roll back. So, I mean, we do support transactions. It's just it's a higher level construct to achieve the transactional guarantees. Did I come close to answering it? Okay. So,
I think we're running out of time.
Okay.
But we can always take more questions afterwards.
Right.
We're going for lunch. If anybody would like to join us.
thank you.